Good day, everybody. This problem is similar to an IMO, that's International Math Olympiad, pinnacle of math competitions. It's similar. The IMO problem wanted you to find all the solutions, and I believe it had a different constant. I think the constant was 7 in that case. I'm wanting to prove there's an infinite number of solutions. Okay, infinite number of solutions. Now, one solution is fairly clear by inspection. The ordered pair, and we're talking about positive this Cartesian product of positive integers, folks. So 11, 11 is a solution almost by inspection, because you see right here, if you put an 11 here and 11 here, folks, you get 11 cubed, right? And then you get plus 2 times 11 right here, right? Y'all, this divides operator means that this guy right here divides this evenly. In other words, you think of it as a fraction that's equal to an integer, okay? Now, in the same thing over here, you get 11 cubed plus 2 times 11. So a number certainly divides itself, right? And again, it's very useful just to think of this as a fraction. It being in the denominator, this being in the numerator, and it being a natural number, a fraction that reduces to a natural number, okay? So we want to show there's an infinite number of such n. We've shown you there's at least one, okay? So let's move along. Now there's quite a bit of algebra right here. Now this idea is a nice idea. I looked at the solution at Papa Flaming's website, and he's the one that, I mean, it's based on something that's clear. It's something that's very, very obvious. If you have integer a divides integer b, again, that's the same thing as saying b over a is just a natural number. This certainly implies that a divides bc, okay, b times c, and that's crystal clear, all right? So that's what we're doing right here. We're using y as our c, so to speak. All right, it turns out that leads to some nice algebra where you get a common factor, and I won't go through all the details of the algebra, but it's kind of clever to try this idea. I wouldn't have thought of it. All right, but once you go through all the algebra, our original expression written as a fraction can be written like this. You see, you get a common factor here of xy squared plus y plus 11 common factor. And so you get this expression. So one way to show there's an infinite number of solutions is just to set this numerator equal to 0. Okay? And it's very clear that when you, that 11n squared, 11n are solutions to this just by looking at it, right? Like if you put 11n squared right here, and I'll just write it directly. If you put 11n squared right here where the x is, this is the x coordinate, this is the y coordinate, right? So you would get 11 squared times n squared, right? Again, and that's physically placing this object right here and just using laws of exponents. And obviously right here you get the very same thing. 11 squared n squared. And so you see, this is what they call by inspection. You can just kind of look at it and see you need a square in there, so the square root business. You don't have to go to the trouble you could solve this and go y is equal to plus or minus square root of x of 11x, but there's no need to do that. Okay, that's certainly equal to 0, right? And so we've proven it, you see, because this n is a natural number. For any n natural number, and that's certainly an infinite set, right? So QED. Now, you may say, well, why? You didn't really prove it because you have to take this and substitute it into the original. And that's what I did down here, folks. And you can come back and look at this if you want, but notice that what happens here, the 11s cancel and you do get a fraction. And I just did, I don't want to drag you through all of this, but I substituted our purported solution into the original expression. And we do get an integer out of the thing. So it works out nicely, and you can come back and review this if you want, or if you just trust me on it. All right. But anyway, let's take a look at some, notice that 1111 is a solution here, right? 1111, we wrote down 1111 is a solution. That would happen when n was equal to 1. let's try maybe n equals to, I don't know, 4, or no, let's make it 5. Make it something a little more. Let's do n equals 5. For n equals 5, you would get 25 times 11 right here. You would get 25 times 11, which is 275. Okay, so that's 275, and then and I'm just doing one special case, and then if you do 5 times 11 right there, you get 55. Okay, so this is just one actual numerical solution that you can check. Okay, but anyway, since n is infinite, and these are it's already been shown that something of this form is shown to be a solution, there are an infinite number. Now, more complex is to consider the case when y squared minus 11x is equal to 0, which is not equal to 0, which is what the competitors in the IMO had to do back in 1998. They actually had to go through and find all the solutions. They had to find the general form for the infinite solutions, and also find there's a few special cases for when this is not equal to 0. Okay, and that it's hard. It's too hard. I'm not sure if I know how to do that. Okay. But anyway, we are done with the problem. There are an infinite number of solutions because there are an infinite number of positive integers. Okay, so that does it. Thank you for viewing.